About the Math 17B first discussion worksheet. So just a reminder, when we first started talking this quarter, the first worksheet was on introducing the concept of integration through a simple example of trying to figure out how much distance you've traveled given your speed and the time you've traveled at that speed. So the problem was, imagine that you and a friend are driving on a highway. Suppose that you wish to determine how far you've traveled, but your odometer is broken. The car's speedometer works, and you have access to a stopwatch. Given these tools, how would you figure out how far you've traveled? Okay, so we began with some simple cases. The first case is if you are traveling at a constant speed. So you're on cruise control, and you can guarantee that you're driving at exactly 60 miles per hour at all times. So in that case, if you drive for 1 hour, you will have traveled 60 miles. Okay. If you travel for half an hour at 60 miles per hour, half an hour at 60 miles per hour, that's 30 miles. And now if you travel for some time t measured in hours, you'll travel 60 t miles. Okay, so if the time is 1 hour, then you'll travel 60 miles, just like in the first case. If we travel for just 1/2 an hour, we'll travel for 30 miles, as in the second case, and t could be anything. Okay, so the next case is, suppose now that we have two constant speeds. So you somehow are able to say that you drive exactly 60 miles per hour for some time, and then exactly 30 miles per hour for some other amount of time. So if you drive for 1 hour at 60 miles per hour, you'll travel 60 miles. And another hour at 30 miles per hour, you'll travel another 30 miles. So total, you'll travel 90 miles. Now suppose instead that you drove half an hour at each of these two speeds. So the first half an hour, you'll travel 30 miles. A half an hour at 60 miles per hour is 30 miles. And then at the next half an hour, you'll travel 30 miles per hour. So that's 15 miles because it's 1/2 an hour at 30 miles per hour. So total you'll travel 45 miles. And notice that this is 3/4 of 60 miles, which was the how far we would have traveled if we traveled 60 miles per hour for the whole hour. And then finally, how far would you go if you travel for a time t1 at 60 miles per hour and a time t2 at 30 miles per hour? Well, you'll travel 60 t1 for the first amount of time, t1, and then you'll travel 30 t2 for the second amount of time. So total, you'll travel 60 t1 plus 30 t2 miles. Okay, the third case is a continually varying speed. So obviously we can't actually guarantee that we travel exactly 60 miles per hour and then exactly 30 miles per hour. So our speed is constantly changing. So now let's suppose that we still have a pretty nice situation in which our speed is linearly decreasing with time. Okay, so our speed v, which is a function of time, is some initial velocity minus at. Here a is our acceleration, or deceleration in this case. Okay, now v0 is our speed at time t0, and a is a positive constant that determines how quickly your speed changes or decreases in this case. Now if a is 0, that means that our speed for all time is just v0. Okay, so our speed is constant in that case. So if a is 0, how far would you go in 1 hour? Well, whatever your speed is, v0 times 1 miles. So v0 miles. In half an hour, now we take our speed v0 times 1/2 v0 over 2 miles. And then in some time t, we take our speed v0 multiplied by t, and that's the number of miles we've traveled. Okay, so that's in the case where we're actually not changing and our speed is just constant again. Okay, so now suppose that v0 is 60 miles per hour and a is 60 miles per hour per hour. So in other words, we start out driving 60 miles per hour, and as time goes on, our speed decreases linearly. So at time t0, you're traveling 60 miles per hour, and at time 1/2, you'd be going 30 miles per hour. And so even though it's not true, we know our speed is changing between those two places, imagine that those speeds were constant over each interval. So we'd be traveling at 60 miles per hour for half an hour, and then 30 miles per hour for a second half hour. How far would we have traveled? Well, this is exactly what we did before. We're going to travel 60 miles per hour for half an hour, that's 30 miles, plus 30 miles per hour for a half an hour, that's 15 miles. So total we'd have traveled 45 miles. Now how does that distance compare with the actual distance traveled, 30 miles? Okay, so this is obviously bigger, and it's actually 1.5 times the actual distance. Okay. Okay, so now, again, supposing that our initial speed V0 is 60 miles per hour and A is 60 miles per hour. Here we're going to say, instead of assuming that we have constant speed over half an hour, let's assume we have constant speed over a quarter of an hour. Okay, so for 1/4 of an hour, we're traveling 60 miles per hour. For 1/4 of an hour, we're traveling 45 miles per hour. And for 1/4 of an hour, we're traveling 30 miles per hour. And for 1/4 of an hour, we're traveling 15 miles per hour. So the total distance we traveled is 60 times 1/4 miles plus 45 over quarter miles plus, over 4, plus 30 times 1/4 miles plus 15 over 4 miles, which is 37.5 miles. Okay, now comparing that to the actual distance that we've traveled, 30 miles, this is 1.25 times 30 miles per hour, or 30 miles. Okay, again, supposing that V0 is 60 miles per hour and A is 60 miles per hour, how did we determine our distance traveled most accurately? Okay, so here's where imagining what the function actually looks like can be really helpful. So I'm just going to bring us down here. Okay, so if we plot on this, the x-axis t, and on the y-axis our speed v of t. So at t equals 0, over here on the y-axis, we intersect at 60 miles per hour, okay? And then we're linearly decreasing, okay? And eventually we're going to hit 0, and the place where we hit 0 is exactly at t equals 1 hour, okay? Because at that point we have 60 minus 60t is equal to 0, so we'd be intersecting this x-axis. Okay, now the distance that we've traveled is represented as the area under the curve on this, speed curve. And so this is a triangle. We can actually get this area exactly. The area of this triangle is 60 times 1 hour divided by 2, right? It's base times height over 2, which is 30 miles. And we've measured that exactly. Okay, so now in reality, we don't actually know how our speed varies with time usually. So instead, suppose that you have, a nice passenger who's willing to measure it for you very frequently, maybe even every minute, for example, in this first case. So suppose that your friend makes the following measurements at the following times. So every minute she's measuring your speed. And if you make the simplifying but slightly incorrect assumption that speed is constant in between the measurements, so for 1 minute your speed is exactly 60 miles per hour, and then in the next minute your speed is exactly 62 miles per hour, and so on, how far would you have gone at time t equals 30? Okay, so we've recorded the speed for every minute, and now in order to say how far we've traveled, we want to find how far we think we've traveled in each minute-long interval and then add them all up. So I'm going to show you an easy way to do this in RStudio. In RStudio, we define almost everything with lists or vectors. So the first thing we're going to do is type in our speed list. Okay, so here I'm saying, okay, computer or RStudio, however you want to think about it, hold on to this list, and I want you to remember that I named it speed. Okay, so this is speed now holds this list, 60, 62, 65. Now this little C out in front is important. It tells the computer, okay, what I'm about to type is a list. I'm going to tell you all of the entries of the list in order, and I just want you to hold on to it. Okay, so now you can see when I hit enter, if we go up and look in our environment, this is where you can see all of the things you've defined, all of the variables you've defined within the computer. When you look in there, you see speed, it tells you the name of it, and it shows you what it's holding. So it says I'm holding numbers that go from 1 to 30, so this is just the length. And here are the first few entries, 60, 62, 65, 68, and so on. Okay, so now the computer knows what speed is. And now, remember, we want to add up all of the distances we've traveled. So what if we just added up all of the things that are in speed? So if we did that, we'd be assuming that, 60, 62, 65, that's how far we've traveled. So that would be if every interval had been 1 hour long. Okay, so I can hit sum speed. This is how you tell the computer to add up all of the things in a list. When I press enter, I get 1,571. So this would be how far we'd traveled if instead of measuring every minute, your friend had measured every hour. So in the first hour, you'd traveled 60 miles per hour. You would have traveled 60 miles, plus 62, plus 65, plus 68, and so on. So we would have traveled 1,571 miles. But we didn't measure every hour, we measured every minute. Okay, so the good news is that every minute is just 1/60th of an hour. So now, instead of saying we've traveled this far, 1,571, we want to instead divide that by 60. Okay, so I haven't named anything here. I'm not having the computer save this, so I have to enter sum of speed that says add up all of the things in speed, and then divide by 60. So this says now instead of imagining we've traveled for an hour, we've only traveled for 1 minute at each of those speeds. So when I hit enter, I get 26.18333. That is the distance traveled in the first 30 minutes. Okay, so we're going to get 26.18333 miles. Okay. Okay, now I want to recreate the plot of the data that we see on our discussion sheet. Now to do so, I already have speed in the computer. So if I look back up into my environment here, I see that speed, the computer already knows what speed is. So I don't need to re-enter that. But I do need to tell the computer what time is. Okay, so if I want to make a plot of speed versus time, or excuse me, time versus speed, I need to define both of those things for the computer. So I'm going to define time by saying t equals sequence from equals 0 to 2 equals 29 by equals 1. Okay, so here I'm defining another list. This is a different way of defining a list. This tells the computer, I want you to define an evenly spaced list, and I'm just going to tell you the first entry, the last entry, and what I want you to count by. Okay, so what you've essentially told the computer is put into a list all of the stuff starting with 0, ending with 29, and counting by ones. Okay, so if I hit enter, I look over into my environment and I see now T is holding a 30 number list that starts out 0, 1, 2, 3, and goes all the way to 29. Okay, so that's good. That's the time intervals that we wanted to keep track of. And now I can plot anything in RStudio quite easily. So I just say plot T, comma, speed. So this is going to make sure that on the x-axis are all of the t values, and on the y-axis are the speed. So that's exactly what we want. We want to plot speed as a function of time. And when I hit enter, here you can see it in the plots area. Okay, now if I want to save that, I can always just hit export and either save as an image or as a PDF or copy it to a clipboard. Okay, so in the previous problem, you assumed that speed was constant between measurements. On the plot below, sketch these assumed speeds in between measurements. These will be horizontal lines of length equal to the interval between measurements and a height equal to the measured speed at the left of the interval. Okay, so of course you would just fill this in, and I'm not going to finish. Okay, as you know, when speed is constant, distance traveled is speed multiplied by time. Thus, for example, the speed traveled in the first interval is 60 miles per hour times 1 minute times 1 hour over 60 minutes. So in other words, we're multiplying the speed times the amount of time in the correct unit that we've traveled. We've traveled for 1/60th of an hour at 60 miles per hour. So we get that we've traveled 1 mile. Okay? This distance can be represented by the area of a rectangle with height equal to the speed and width equal to the time interval. Sketch in each of these rectangles in the previous plot. Since each rectangle's area is the distance traveled in that interval, given the area of each rectangle, how would you determine the total distance traveled over the full 30 minutes? Okay, so of course if we take all of these little rectangles that we draw, we're just going to get the full distance that we've traveled, or at least an approximation of it, we want to add all of these up. Okay, so notice here the width of the rectangle is always 1 minute. So all of these are constant 1 minute. And then the speed is the height of the rectangle. So once we have the area of this rectangle, we have the approximate distance we've traveled for that 1 minute. And to get the total distance, we just add them all up. Okay, so we're going to sum them. The distance traveled is represented by the area under the curve of speed versus time. By assuming that speed is constant in each interval, we can easily estimate this area. Can you think of a different assumption that would allow you to estimate this area more accurately? Okay, so what we're thinking about here is, so we've been making this nice assumption that everything we can approximate really well with rectangles, right? And that's absolutely true. Rectangles work great. But suppose you want to get a little bit more accurate, right? So say you have something really dramatic. You have a speed and one at time t1 here and time t2 that's quite different. So obviously if we use the left endpoint and we represent it with a rectangle of this height, we're overestimating quite a bit because whatever the function's doing in this interval, it must be decreasing somehow. And if we were to use the right endpoint, we would underestimate by a lot. So what we can do is instead just say, let's suppose that in this interval, the speed is decreasing linearly with time. Okay, so that would give us this nice line connection between these 2 points. And then this is actually a shape that we can get the area of quite easily. This is a trapezoid. Okay, and so this way of thinking leads to the trapezoidal rule.